Hello, my calc babies. Today we're going to be talking about the epsilon delta definition of the limit. I've heard some people call it delta epsilon. Epsilon delta works fine, either or. Last time we talked about the informal definition of the limit, which was f of x gets arbitrarily close to some L as x gets arbitrarily close to some C. And although this may look very formal, it still has no definition for what arbitrarily close means, and that is what we're going to be exploring today. So we're going to be using this function here as a reference to what we're talking about. And we're going to imagine this line right here as our f of x. C is going to be the number that we're approaching on our x-axis, and L is going to be the number that we're eventually going to find. Given that there's a hole in our graph at C, we need to use limits to figure out what this L value is. The graph we have right here is the same graph we have over here if we were to have zoomed in really close to the graph at this area where x is equal to c. If you remember from our last video, we used calculators to see what would happen to our value as our x's get really close to some value, c. For example, if we had a hole at 1, we would plug in zeros like 0.99999 or even 1.00001. This here is a similar number. We're trying to approach C from the left-hand side and the right-hand side. If we were to imagine that C is equal to 3 and delta is equal to 0.1, it'll look fairly familiar to what we were doing last time. Say the left-hand side would be C minus our delta, which would be 2.9, and on the right-hand side we'd have C plus delta, which would then equal 3.1. So as we add these tiny little nudges to our x as it approaches C, mainly this delta up here, we'll get these tiny little nudges right here in our y direction, which we'll call epsilon. You can also notice that we are very close to this L, mainly just epsilon units away from L, but we can't actually get to L from C. So we want to see the values that it approaches using these tiny nudges, and that's the idea of what limits are. Let f be a function defined on an open interval containing C, except possibly at C, and let L be a real number. The statement that the limit as x approaches C of f of x is equal to L means that for every epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus c less than delta, then the absolute value of f of x minus L is less than epsilon. In layman's terms, if you can find an epsilon right here, just that, if that's greater than 0, then you can find a delta greater than 0 that exists as well. So this. What we're going to be doing now is going over some examples to give you a better understanding of what that all actually means. So here's our first example. It says, given the limit as x approaches 3 of 2x minus 5 is equal to 1, find a delta such that the absolute value of 2x minus 5 minus 1 is less than 0.01 whenever our 0 is less than the absolute value of x minus 3 is less than our delta. So it's a good thing to start with noting what variables that you do have. So here we can notice that our x approaches some c, our c being 3. Our L is 1. Our f of x is 2x minus 5, our epsilon is 0.01, and our delta is still unknown. That is what we're going to be looking for. We're going to be using the formal definition of the limit to be able to solve for delta. So what you want to take note of is that the absolute value of f of x minus L is less than our epsilon, and that the absolute value of x minus c is less than our delta. So if we take note of all the stuff that we gathered from the question itself and plug it into our formal definition of the limit, we can get to these two inequalities that we'll need to solve for our delta. Alright, I wrote down the absolute value of 2x minus 5 minus 1 is less than 0.01 on one side and the other on the other side. So the first step that we'll have to do is simplify everything that's in there. So 2x minus 5 minus 1 without parentheses evaluates to 2x minus 6 is less than 0.01. Then we can pull out the 2 in front of the absolute value sign because 2 is positive and multiplying anything that's positive by positive is always going to be positive. And then we're going to divide the 2 on both sides, so we're going to get x minus 3 is less than 0.01 over 2. If you notice here, we have an x minus 3 is less than some number over here, and then we also have x minus 3, which was our x minus c, is less than our delta. Well, we have this looking exactly like that side. So that must mean that our 0.01 divided by 2 is actually our delta. So graphically, you can see our function f of x of 2x minus 5 is graphed right here. But if we were to zoom into this one spot right here where our x is 3, then you can see that when the epsilon is equal to 0.01, we have 1 as our L, 1.01 because it's 1 plus our epsilon, and then 0.99 because it's 1 minus our epsilon. What we were looking for is that delta, that small nudge in the x-axis. Alright, that was it for chapter 1.2 of the textbook. Next video we'll be going over chapter 1.3, which goes over evaluating limits analytically. So if you guys like this video, please give it a like and think about subscribing. Alright.